If you've ever been confused about the difference between a damp-proof membrane and a damp-proof course, you're certainly not alone. These two terms are often used interchangeably in casual conversation, but in professional construction practice, they represent two distinct components with specific roles in a building's moisture management system. Understanding this distinction isn't just academic, it's fundamental to creating durable, healthy buildings that stand the test of time. In this comprehensive guide, we'll dive deep into both systems, exploring their individual characteristics, their synergistic relationship, and the critical importance of getting both right from the foundation up. Let's start with the fundamental science that makes both DPM and DPC necessary: capillary action. This physical phenomenon occurs when liquids spontaneously rise in narrow spaces without the assistance of, or even in opposition to, gravity. In building terms, think of your masonry materials: bricks, concrete blocks, mortar as containing millions of microscopic tubes. When these materials contact moist soil, they naturally wick moisture upward through these capillary channels. This rising damp carries not just water but also soluble salts from both the ground and the construction materials themselves. When the water eventually evaporates from wall surfaces, these salts crystallize, creating the classic visual signs of moisture problems: tide marks, blistering paint, and crumbling plaster. The strategic placement of impermeable barriers, DPM and DPC, breaks this capillary action, creating what building scientists call a capillary break. Now let's examine the damp-proof membrane in detail. The DPM serves as the horizontal barrier that separates your concrete ground floor slab from the moisture-containing ground beneath. Think of it as the bottom of a waterproof box that contains your building. Typically made from low-density polyethylene LDPE with a minimum thickness of 1200 gauge 300 microns, the DPM creates a continuous impermeable layer that prevents ground moisture from migrating upward into your floor slab and subsequently into the building interior. The installation process for a DPM is methodical and requires precision. It begins with a properly prepared sub-base of well-compacted hardcore, followed by a blinding layer of sand to create a smooth, stable surface free of sharp protrusions. The polyethylene sheet is then rolled out with minimum 150 mm side laps and 300 mm end laps, all meticulously taped with specialized DPM tape to ensure complete continuity. A crucial pro tip from experienced site supervisors is to always place a protective layer, typically a sand blinding or specific protection mat, over the DPM before pouring concrete. This prevents the sharp edges of aggregate in the concrete mix from puncturing the membrane during placement and vibration, a failure that is virtually impossible to detect once the concrete has cured but can compromise the entire system. The damp-proof course, while serving a similar moisture-blocking function, operates in a completely different location and context. Where the DPM protects horizontally beneath your floor, the DPC protects vertically within your walls. Installed typically 150 mm above finished ground level, the DPC creates a horizontal barrier within masonry walls that prevents moisture from rising upward from the foundation into the wall structure. Modern DPC materials have evolved significantly from the early slate and lead sheets used historically. Today, you'll most commonly find flexible DPCs made from polyethylene, polyvinyl chloride PVC, or sometimes bituminous felt. These materials come in roll form and are laid entire courses in mortar beds during wall construction. The critical installation factor for DPCs is continuity. The barrier must run uninterrupted through the entire thickness and length of the wall, including at corners and junctions. Any break, tear, or puncture compromises the entire system. Another essential consideration is the step-down detail at door and window openings, where the DPC must transition downward to maintain protection around these vulnerable penetrations. A common and costly on-site mistake is when bricklayers cut the DPC to fit around obstacles rather than properly detailing these transitions, creating permanent pathways for moisture intrusion. The relationship between DPM and DPC isn't just complementary, it's symbiotic. For a building to be truly protected from ground moisture, these two systems must work together as a unified whole. The critical connection occurs at the perimeter, where the DPM, turned up at the edges, must lap into or connect seamlessly with the DPC in the walls. This creates what moisture management specialists call a tanked or tray system, a complete moisture-proof enclosure that separates the entire habitable space from the moisture-laden ground. Beneath and or on it, this connection is so vital that building codes explicitly require it. Though the specific detailing may vary based on foundation type and wall construction. In cavity wall construction, for instance, the DPM typically connects to the inner leaf DPC, while the outer leaf has its own separate DPC that directs any moisture that penetrates the facade back to the exterior through weep holes. This sophisticated coordination of multiple barriers demonstrates the complexity of modern moisture management and underscores why understanding both DPM and DPC is essential for construction professionals. Despite their importance, both DPM and DPC systems are vulnerable to specific failure modes that every builder should recognize. The most common issue is bridging, where a material creates a pathway for moisture to bypass the impermeable barrier. For DPCs, the most frequent bridging occurs when mortar droppings accumulate in cavity walls during construction, creating continuous material connections between the outer and inner leaves that effectively short-circuit the DPC. External render applied below DPC level or soil and paving build-up above it similarly create bridges that defeat the purpose of the barrier. For DPMs, besides puncture during concrete placement, the most common failures occur at surface penetrations where pipes and cables pass through the slab. Without proper sleeving and sealing with flexible, non-hardening sealants, these penetrations become direct conduits for ground moisture. Another significant challenge is thermal bridging at perimeter connections, where the continuity of insulation is broken at the DPM/DPC junction, potentially leading to cold spots and condensation issues even when rising damp is properly controlled. The consequences of DPM and DPC failures extend far beyond cosmetic concerns. Persistent moisture intrusion leads to deterioration of building materials, corroding metal fasteners, rotting wood elements, and degrading masonry through freeze-thaw cycles. The elevated moisture levels create ideal conditions for mold growth, which poses significant health risks to occupants through poor indoor air quality. The soluble salts carried by rising damp not only cause visual damage but can also lead to efflorescence and cryptofluorescence, where salt crystallization within the pore structure of materials creates internal pressures that can spall surfaces and reduce structural integrity over time. From a building performance perspective, damp walls have significantly reduced thermal resistance, leading to increased energy costs for heating and cooling. The comprehensive understanding of both DPM and DPC systems, their proper installation, and their maintenance is therefore not just a construction best practice but a fundamental requirement for creating healthy, durable, and efficient buildings. To summarize the key distinctions, the damp-proof membrane is your horizontal ground moisture barrier beneath concrete floor slabs, typically a polyethylene sheet installed before concrete placement. The damp-proof course is your horizontal moisture barrier within masonry walls, typically a flexible strip material installed during wall construction approximately 150 mm above ground level. While they serve the same fundamental purpose of preventing moisture rise, they operate in different planes, require different installation techniques, and face different failure modes. Most importantly, they must work together as a continuous system to provide complete protection. Now, I'd like to hear from your experience. What's the most challenging DPM or DPC installation you've encountered? Have you discovered innovative solutions for connecting these systems or dealing with difficult site conditions? Your practical experiences in the comments below will help build our collective knowledge. If you found this deep dive into moisture management helpful, please like this video and subscribe.